Metal organic frameworks, or MOFs, are the cutting edge of adsorbent materials and have the potential to revolutionize important scientific industries such as carbon capture and drug delivery that depend on adsorptive materials for their success. Preparing MOFs for such applications, however, can be a very difficult process. Today, we propose a way to improve the feasibility of using a modification called ligand installation upon this class of compound to impart MOFs with the desired properties essential for their subsequent use in a targeted field. MOFs are constructed from positively charged clusters of metal ions which are bridged by organic linkers. Many properties of a MOF can be modified in order to impart them with new functionalities. Ligand installation is a type of modification that involves specifically designed ligands being installed on the parent MOF structure. This yields new MOFs with new functions depending on the ligand that was installed. Studying reaction pathways is key in determining how to optimize a ligand installation, since these show the evolution of a system over time. However, there is currently no way to monitor a complete MOF reaction pathway. The current approach in characterizing them is to use X-ray diffraction or solution NMR to analyze the MOF before and after the reaction. The disadvantage of X-ray diffraction is that it cannot monitor the MOF during the reaction pathway or detect how the ligand is installed. Moreover, solution NMR destroys the MOF, so it also cannot be used to monitor the reaction pathway. Our proposed solution is to use solid-state NMR to monitor entire ligand installation reaction pathways. The advantages of SSNMR over other methods are that it does not destroy the sample during the monitoring process and provides a detailed structure of the molecule during the reaction, which allows for the reaction conditions to be adjusted if necessary in order to improve the final product. There is evidence that supports the feasibility of our idea. Several studies have obtained high-resolution spectra in 10 to 20 minutes. We define high-resolution spectra as those where we can resolve peaks for CH, CH2, and CH3 groups, as distinguishing between these peaks allows us to observe changes upon the MOF. The specifications used by the other studies which are alike to ours are the use of solid-state samples to preserve the MOF structure, a 10 to 20 torr magnetic field, and very fast magic angle spinning to achieve a high resolution so that changes to the MOF can be distinguished, and the use of specific pulse patterns for the applied magnetic field, such as the depth sequence, that effectively suppresses the background noise. The MOF industry is forecasted to nearly quadruple in economic worth from $250 million to $1 billion within 8 years. As such, MOFs have the potential to revolutionize many fields, including medicine and carbon capture in the near future. However, in order to enable the widespread use of MOFs in these fields, we must first have a comprehensive understanding of reaction pathways involving these adsorptive materials. Our proposed solution provides a means to optimize the preparation of MOFs for their subsequent use in many fields, and this in tandem with the high designability of these compounds will help to serve as the basis for important future technologies.
Created using Powtoon.